Hello, welcome back to the class. So let us solve some examples today. Write down the first problem. The problem goes like this. A short RC column, 400 millimeter by 400 millimeter is provided with 8 bars of 16 millimeter diameter. If the unsupported length of the column is 2.25 meter, find the ultimate load capacity of the column. Use M20 concrete and Fe 415 steel. Solution. So let us read the problem. A short RC column. See, look at the problem. It says a short RC column. If it did not say a short RC column, you should check whether the column is short or not. How do you check? L effective, that is the effective length of the column, divided by the lateral dimension, find out that should be less than 12 for the column to be short. Okay? Then only you can make use of certain formulas. If it is long, then you will have a set of different formulas you need to follow. So in this case, the first step is you check whether the column is long or short. Make sure that is short. But here I am not going to check it because the problem itself says it is a short column. Is it clear to you? So what are the dimensions of the column? 400 millimeter by 400 millimeter. That is a square column. Is provided with 8 bars of 16 millimeter diameter. So if the unsupported length of the column is 2.25 meter, that is the total length of the column. That is from the top of the floor to the bottom of the beam. What is the length of the column? That is the unsupported length, and I have discussed this part before already. Okay, is 2.25 meter. Find the ultimate load capacity of the column. Use M20 concrete and Fe 415 steel. So please write down this figure. The column is like this. So how many bars we have? 8 bars. Okay. So these are the 4 bars, and we have another 4 bars of the same diameter. We are going to place like this. And of course, when we are providing lateral ties, we are going to provide lateral ties like this. If the size is What we do is, we are going to provide lateral ties like this, or again, depending on the type of the column, importance of the work, the kind of load it is carrying, we may provide some additional lateral ties to put these 4 bars together. So it is going to be like this. Okay. So I am not worried about the lateral ties in this problem, because this lateral ties for this problem is immaterial. So this is 400 millimeter, and this is 400 millimeter. So the first thing we need to do is, we need to check for the minimum eccentricity. So please open page number 42, 25.4 of the code book. I am going to read that paragraph. So all columns shall be designed for minimum eccentricity equal to the unsupported length of the column divided by 500 plus lateral dimensions divided by 30. So it's subject to a minimum of 20 millimeter. Okay. So I am going to stop at that sentence. I am not going to go with the second sentence, because we are not there yet. We are going to discuss about the second sentence in future in this module. Okay. So minimum eccentricity should be higher of the following 2 values. That is 25.4, page 42. One is L divided by 500 plus lateral dimension. In this case, you call it as small d or b. It is one and the same, because it is a square one. It has the same dimension. This is the least dimension, at the same time this is the biggest dimension. So L by 500 plus d by 30. That is what the code says. That is the sentence I read just now. So what is L? L is the unsupported length. So what is the unsupported length? Yes, it is given that the unsupported length of the column is 2.25 meter. So that is equal to, L is 2.25 multiplied by 1000, convert this value into millimeter, divided by 500 plus d by 30, that is 400 is the lateral dimension of the column, divided by 30. Okay. So this is going to be 4.5 plus 13.33 equal to 17.83 millimeter. Okay. And also, it should not be less than 20 millimeter. So take higher of these 2 values as the minimum eccentricity. So what is the minimum eccentricity we have to design, or we have to check the column for? So it is going to be 20 millimeter. Therefore, E minimum is the higher of these 2 values, that is 20 mm. Okay. Next, to find out the capacity, that is the ultimate load capacity or design strength of the column, we need a formula. So for that, please go to page number 71 of the code book. Please go to page number 71, and at 39.3 it says short axially loaded members in compression. Short. So whatever the formula given under this is for a short column. So we are dealing with a short column because the problem itself says it is a short column. Then it goes in this sentence like this: the member shall be designed by considering the assumptions given in 39.1, okay, you don't worry about it, and the minimum eccentricity, full stop. Minimum eccentricity we have checked, that is 20 millimeter eccentricity. When the minimum eccentricity as per 25.4 on page 42 does not exceed 0.05 times the lateral dimension, the members may be designed by the following equation. What it means is, so as per this, I am going to check what is the value of 0.05 multiplied by the dimension of the column. So as per this 39.3, page 71, 0.05D equal to 0.05 into 400, that is equal to 20 millimeter. Okay. So look here, look here. So as long as this value is less than or equal to at most this value, then we can go ahead and make use of the formula given under 39.3. So in case if E minimum exceeds 20 millimeter, say for example we got this value equal to say 22 millimeter, okay. If this is 22, this is 20, so higher of these two values is 22, that is the minimum eccentricity you need to go for. So here it is 20 mm, when 22 millimeter exceeds this 20 mm, then we cannot make use of the formula given in 39.3 on page 71. In this case, this value should be less than or at most equal to 20 mm. Of course, in this case E minimum is equal to 20 mm. So what we can do is we can make use of the formula given in 39.3. So I am going to write here E minimum should be less than or at most equal to 0.05D. So what is the E minimum value? 20 should be less than or at most equal to 20 mm. That is 20 mm and 20 mm. So this equal condition is satisfied. Therefore, we can make use of the formula PU, that is the design compressive strength or ultimate compressive strength strength. So what is it? Does it call PU? PU equal to, I'm going to write this, the next line, PU equal to 0. Excuse me, 4 FCK and AC, that is the area of concrete, plus 0.67 Fy and ASC, that is the area of compression steel. Of course, FCK is 20 Newton per millimeter square, that is the concrete we are using, M20 concrete, and for Fy it is 415 steel, that is again given. So let us find out what is the area of steel first. So how many bars we have? We have 8 bars of 16 mm dia. So let me call this as equation 1. So area of compression steel ASC equal to 8 bars pi by 4 16 square. Okay. So that value is going to be 1608.5 millimeter square. That is the area of compression steel. Next, so what is the area of concrete? So area of concrete AC equal to, see, look at the plan here. This is the sectional plan. When you look from the top, you see this column and we see 8 bars. So what is the area of concrete? The area of concrete is the total area minus the area of cross section of these main bars. Okay. So area of concrete is 400 by 400, that is the gross sectional area. I am going to write AG minus area of compression steel. So what is AG? That is the gross sectional area, 400 by 400 minus, so area of compression steel is 1608.5. Okay. So that is going to be, AC is 158,391.5 millimeter square. That is the area of concrete. So if we come to equation 1, FCK is known, Fy is known, that is given. Area of concrete is this, and the area of compression steel is this. Substitute all the values in the equation 1. So we are going to get Pu value. So by substituting, the values in equation 1, we get Pu equal to 0.4 FCK. 4 into FCK is 20 and area of concrete is 158,391.5. Okay, plus 0.67 into 415 into area of compression steel, that is 1608.5. So I am going to get these values in Newton. So I am going to convert the values into kilonewton by dividing by 1000. So if I take the values individually, I am going to get 126,7.23 plus 447.24, that is Pu equal to 1714.47 kilonewton. That means the design strength or the ultimate compressive strength of the concrete part of the column is 1267.23 kilonewton and the steel part of the column is 447.24 kilonewton. Okay, and the total is 1714.47 kilonewton. So approximately it is 126 or 127 tons. This is 45 tons. Okay, that means steel is going to carry around 45 tons and the concrete is going to carry around 127 tons of the design load, okay, because that is design load in the sense this is the load that is going to cause failure of the column, okay. Therefore, what the problem says, find the ultimate load capacity of the column. Therefore, ultimate load capacity of the column equal to 1714.47 kilonewton. Okay, this completes the problem. So next one is another problem. Let us go with the next problem. A reinforced concrete short column (400 mm by 400 mm) has to carry an axial load of 1200 kilonewton. Find the area of steel required. Full stop. Use M20 concrete and Fe 415 steel. Solution. So, a reinforced concrete short column 400 mm by 400 mm has to carry an axial load of 1200 kilonewton. So, find the area of steel required. Use M20 concrete and Fe 415 steel. So, what is the size of the column? It is 400 millimeter by 400 millimeter. Okay, and it says it is a short column. Then we can make use of the formula given under 39.3 on page 71. So, what is the load it has to carry? That is 1200 kilonewton. That is the service load. So, the load, the column has to carry is P, that is equal to 1200 kilonewton. Therefore, the ultimate load or the design load or the factor load is Pu, that is equal to 1.5 times is the load factor multiplied by 1200, that is equal to 1800 kilonewton. So this is the load for which we need to design the section. Here of course the section dimensions are fixed, it's already given, and we need to find out only the area of the steel. So of course use M20 concrete and Fe 415 steel. Here the problem is we need to find out the minimum eccentricity for which we need to design. So what is the minimum eccentricity? L by 500, where L is the unsupported length, plus D, that is the lateral dimension, divided by 30. So we need to find out, and of course this should not be less than 20 millimeter. So two values. But the problem here is we cannot find out this. The reason is we don't know what is the length or unsupported length of the column. So it is not given in the problem. So we don't worry about this part. So we directly jump to the formula and we are going to find out what is the area of steel required. So we have Pu equal to 0.4 FCK multiplied by the area of concrete plus 0.67 Fy multiplied by the area of compression steel. So what is Pu? In place of Pu, I am going to substitute this value. So that is 1800, and I am going to convert this value into Newton, that is equal to 0.4 multiplied by FCK, Newton per millimeter square. And what is AC? Area of concrete is the gross area AG minus the area of compression steel. We don't know what steel we are going to get here, what area, what diameter, how many bars, what are those diameters, we don't know. But the total area of compression steel is ASC, which we are trying to find out. And the total area of this section is 400 by 400. So 400 by 400 is the gross sectional area minus area of compression steel will give you the area of concrete plus 0.67 multiplied by 415 multiplied by ASC. Again, that is the area of compression steel which we are going to find out. Okay. So here what is the unknown? ASC is the unknown. So we can find out what is ASC. After simplification, therefore ASC equal to 1926 millimeter square. That is the minimum area of compression steel required. So we can provide 4 bars or 8 bars. Okay, it is better because it is a square section, it is better we provide reinforcement equally on all 4 sides. So what I do is, let us provide four of 20 mm dia and 4 of 16 mm diameter. Okay. Therefore, actual area compression steel provided equal to 4 of 20 mm plus 4 of 16 mm. So that is ASC actual is given by, that is 2060 millimeter square. So this is greater than the actual, the required area of compression steel, 1926 millimeter square, therefore okay. So can we not provide 8 bars of 20 mm diameter? Yes, of course we can provide, but this is going to be greater than 2060, that is 2060, then the section is going to be adequate, but the problem is the section is going to be uneconomical. Okay. And can we provide 8 bars of 16 mm? Yeah, you can try 8 bars of 16 mm, and the area you are going to get will be less than 1926. So 1926 is the minimum area of compression steel required. So 8 bars of 16 mm is not adequate. So 8 bars of 20 mm is too much. That is the reason we are giving 4 bars of 20 mm and 4 bars of 16 mm. So before deciding, you need to do little bit of calculation on the margin and then provide these reinforcements. Okay. So here at the corner I am going to provide 4 bars of 20 mm diameter bars, that is 4 bars of 20 mm dia, and here I am going to provide another 4 bars of 16 mm dia. So it is 4 bars 20 mm dia, and these bars, that is 4 of 16 mm dia. Okay. Next I need to provide lateral lateral ties. Before that I need to check for minimum area of compression reinforcement and also maximum area of compression reinforcement. So to check for ASC minimum, this is as per 5.3.1a, page 48. 5.3.1, page 48. So as per this clause, that is 26.5.3.1 on page 48, ASC minimum is 0.8% of the gross area. 0.8% of the gross area is 400 by 400. Okay, 1600, that is 1280 millimeter square. Okay, this is the minimum area of steel required, and ASC provided is 2060 millimeter square is greater than ASC minimum. This is ASC minimum. Therefore, okay. Okay. So what in case actual ASC is less than 1280? Say for example, we got this value equal to 1100 millimeter square. Then in such case, what we do is we go ahead and provide a minimum of 1280 millimeter square. Is it clear to you? So similarly, to check for ASC maximum, that is again as per 26.5.3.1 page 48. So ASC maximum is 6% of the gross area, that is 400 multiplied by 400. That is equal to how much? That is 100 cancelled. That is 9600 millimeters square. Okay. So ASC actual is less than ASC maximum. Therefore, okay. So what if ASC you are providing exceeds ASC maximum of 9600 millimeters square? In such case, what we do is, whatever the section we have provided is not adequate, go ahead and redesign this section. That means you increase the dimensions of the column. Okay. So in this case it's okay. Whatever value we got is greater than ASC minimum required, and again, and it is less than ASC maximum allowable. Is it clear to you? So next comes lateral ties. So lateral ties we are going to provide as per 26.5.3.2c, 26.5.3.2c, page 49. So let us fix the diameter of the lateral ties first. So one is the diameter. Okay. So the diameter of the lateral ties should not be less than 1/4 of the dia of the largest bar. That is equal to. So what is the diameter of the largest bar here? We are using two types of bars, that is, one is 16 millimeter, 416 millimeter, and the other is 20 millimeter. So the largest bar is 20 mm, that is 1/4 of 20 is 50 millimeter. Okay. Next, and the other is 6 millimeter. If you refer the code, you are going to see these two things. Okay. So out of these two, take the higher value. Therefore, we shall use 6 millimeter dia lateral ties. Next, what is the spacing of lateral ties? Spacing. So spacing should not exceed the following cases, that is, least lateral dimension, so what is the least lateral dimension? Here it is a square section, so you take to 400, 400. So the least lateral dimension is equal to 400 millimeter itself. Okay. Then the 16 times the dia of the smallest longitudinal bar. The smallest bar, that is equal to 16 times 16 is the dia of the smallest bar. So that is 256 millimeter square. And also the code says in no case the spacing should exceed 300 millimeter center to center. Okay. So we have three values, 400, 256 and 300. Take least of these three values. So what is the spacing of lateral ties we are going to give? We are going to give at a spacing of 256 millimeter center to center. Of course, we are not going to give at such fractional values. Instead, we are going to give at a spacing of 250 millimeter center to center. So what is the diameter of this one lateral ties? That is 6 millimeter. So what is the spacing of lateral ties? That is at least 256 millimeter center to center. Not at least, at most. So therefore, we shall provide 6 millimeter dia lateral ties at 250 millimeter center to center. Okay. So this completes the problem. Afterwards, so you show everything in a drawing, that is the reinforcement details. This is sectional plan. Okay, this is sectional elevation. Okay, so these are the bars. At the end we have (20 mm) dia bars at the corner, and these 16 millimeter dia bars we cannot see when you look from this side, so they are hidden. So, however, we can see this bar. So 6 mm dia lateral ties at 250 millimeter center to center. Okay. So these are (6 mm) dia lateral ties at 250 millimeter center to center. Okay, and of course we are providing one more set of lateral ties. It is recommended. Okay, again these bars at a spacing of 250 millimeter center to center. That is this one and this one. Okay. So these are the main bars. So 4 of 20 mm dia, and this is again 4 of 16 mm dia. So this completes the problem. Please write down. So, thank you, and we will go with the next problem in the next class.